Good morning. My name is Steve Jagels, and I'm the Global Market Manager for Oil and Gas with Precision Polymer Engineering and IDEX Company. Today's webinar is entitled Low Temperature Sealing in Sour Gas. We have seen a trend over the years towards higher pressures, higher temperatures, lower temperatures, and resistance to multiple chemicals, including sour gas. While it hasn't been a problem to address a few of these conditions, it has been a problem to address all of these factors with one material. Most notably, obtaining a material that had low temperature elasticity and sour gas resistance at the same time. The agenda for today's webinar will be a brief introduction to IDEX sealing solutions and precision polymer engineering. I'll review sour gas resistant elastomers, test methods, and test results. I will also look at low temperature testing of elastomers, their test methods, and some test results. And I'll finish with a few case studies and summarize with some conclusions. Let's get started with some information about IDEX Sealing Solutions. IDEX Sealing Solutions is a business unit of IDEX Corporation, which is traded on the New York Stock Exchange as IEX. IDEX Sealing Solution is composed of three companies: Precision Polymer Engineering, with locations in Houston, Texas, and Blackburn, UK. There's FTL Technology, located in Leeds, UK, and the newest member of IDEX Sealing Solutions, Novotima, located in Villano, Italy. Now, each of these business units provides complementary manufacturing, seal engineering, and seal technology to address critical sealing applications in the oil and gas market. Many of the solutions provided are highly customized to a particular application. Here are just a few examples of the critical seals made by IDEX Sealing Solutions. There are O-rings, elastomer spring seals, PTFE spring energized seals, PTFE shaft seals, and a full range of specialized geometries. We supply seals for use in equipment such as compressors, pumps, valves, and downhole tools. IDEX Sealing Solutions markets elastomer materials for oil and gas applications under several brands, including Endura, Perlast, and Perlast Ice. Endura materials are specially compounded for resistance to high pressures and rapid gas decompression. Perlast is our perfluoroelastomer brand for extreme temperature and chemical environments, and Perlast Ice is a range of FFKMs for low temperature and pressure cycling with aggressive chemicals. Now let's get started by learning about sour gas resistant elastomers. In the following slides, I'll list the major industry specifications for sour gas resistance for elastomers and then show some H2S testing on several elastomer types with data. Sour gas can be a problem almost anywhere. The graph on the right shows various crudes around the world and their associated sulfur content. Any crude over 0.5% of sulfur would be considered sour. And typically a higher sulfur containing crude will have had more H2S in the well or the production stream. Now, H2S is often associated with sulfate reducing bacteria or decomposing organic matter that can turn a previous sweet well sour if contaminated. Regardless of where the H2S came from, it is a concern for many oilfield engineers due to its toxicity and potential for reacting with metals and polymers, creating the potential for dangerous leaks and environmental contamination. Most equipment manufacturers find it to their benefit to supply seals that can handle the widest range of environmental and chemical environments. Turning to the industry specifications for evaluating elastomers in sour gas, there are a few specs that are most often cited. They are NORSOK M710 Annex A, ISO 23936, which is related to the NORSOK specification, ISO 10423, or API 6A, and NACE 0187. Of the specifications cited, NORSOK M710 is perhaps the most aggressive and most widely used for testing elastomer performance. NORSOK M710 will be the basis of the test procedure and resulting data that will be shown later in the presentation. As mentioned in the beginning of the presentation, there are trends in the oil and gas market requiring higher temperatures, higher pressures, lower temperatures, and sour gas resistance. Reviewing ASTM D2000, we can see that polymers normally are ranked based upon oil resistance and high temperature resistance. We can see that these polymers increase in oil resistance moving to the right and improving in upper service temperature moving up on the chart. Since we're discussing elastomers in the oil and gas industry, we are really limited to a few available polymer classes, namely HNBR, FKM, FEPM, and FFKM. The chart unfortunately does not go far enough and provide us an indication of sour gas resistance or low temperature sealing performance. In fact, within these general polymer types, the performance in sour gas and low temperature performance can vary greatly. The test data that will be shown today is all performed on commercially available compounds. I've listed them generically and by the specific material. There is a low temperature HNBR Endura Z85L, a peroxide cured FKM Endura V91J, an FEPM Endura A90H, a FFKM Perlast G92E, and a low temperature FFKM Perlast Ice G90LT. Each of these materials are high durometer materials designed for and sold into the oil and gas market currently. The first test I'll show of a material in a sour environment will be a low temperature HNBR Z85L. It was tested near its high temperature service limit, and then the next slide will show the higher temperature materials. The test generally follows the Norsok M710 Annex A protocol. The test specimen is immersed in a multi-phase mixture containing a gas component, hydrocarbon mixture, and water. The y-axis is the ultimate elongation of the test sample as it is aged in a fluid over the length of time as described on the x-axis. The elongation at break is a good way to measure the effects of sour gas on an elastomer, as there normally will be embrittlement and it is easy to visualize what is happening to the material over the test time period. In this example, the initial loss of elongation is most likely from the sample's uptake or absorption of the hydrocarbon fluid. Midway through the test, there's some increase in the elongation, which may be some additional cross-linking of the material from the H2S, but this is followed by a steady decline in the elongation as the sample starts to become brittle and react with the hydrogen sulfide. This graph shows the higher temperature fluorocarbon elastomers. Here we have a test at 200 degrees Celsius versus the 155 degrees C as we saw in the previous slide. The higher temperature allows us to observe property changes faster and provide a level of confidence that the material will be suitable in a similar service environment. As before, the ultimate elongation of the sample in percentage is on the y-axis and the time in hours is on the x-axis. The materials tested are a peroxide cured FKM Endura V91J, an FEPM Endura A90H, an FFKM Perlast G92E, and a low temperature FFKM Perlast Ice G90LT. This really is a good representation of high quality elastomers used today in critical service. What's immediately obvious is that the FKM, represented by the solid line, exhibited significant change throughout the test period. He has a rapid rise in elongation that is followed by a rapid decline. At the end of the test, the sample is brittle and no longer elastomeric. In a critical seal that is expected to last for many years, stability of properties is key. The other three materials tested have relatively stable ultimate elongations. We therefore observe that FEPM, FFKM, and low temperature FFKM are generally non-reactive in a sour environment. As a summary, I've listed out some elastomer types by family and their characteristics in sour service, high temperature performance, and as a preview of subsequent slides, low temperature performance. There are a few additional elastomer types shown here in which I did not show data for the purposes of simplifying today's presentation and time constraints. On the first row is a rating for sour service from 1 to 3, 1 being best. Of the elastomer types listed, only FEPM, FFKM, and low temperature FFKM show very little reaction or change in sour service. The second and third rows show the lower temperature limit, followed by the third row with the upper temperature limit. Of the 3 materials with a run rating for sour service, 2 have low temperature ratings near the freezing point of water, which can limit their usefulness in many applications environments. We'll go into more detail on low temperature characteristics of elastomers in the next part of the presentation. Now let's move on to low temperature performance of elastomers. In the next part of the presentation, we'll examine the low temperature test methods of elastomers and the low temperature capability of the sour service resistant materials we have just reviewed. As indicated by the diagram at the bottom of the slide, we are now past the halfway point of the presentation. There are a number of different test standards for low temperature performance of elastomers. They are ASTM D1329, which is the temperature of retraction test, ASTM D2137, which is the determination of low temperature brittleness, ASTM D7426, the determination of the glass transition by DSC, ASTM D1053, which is the Gaiman test, and ASTM D1229, which is the determination of compression set at low temperatures. I believe one of the most reliable tests is the determination of the glass transition by DSC, which is the ASTM D7426. As we saw in the previous slide, there are a number of test methods, and as you might expect, they will give different results. As an example, if we tested our perlast ice, low temperature FFKM, we would find different results. We could, for example, flex the material around a mandrel and it wouldn't break at minus 40 degrees C. The temperature of retraction would have a different number, and the DSC glass transition would be yet another number. The main point is that there is some variation in the test methods and the results, so that we should look for large differences among materials to guarantee the seal will function at very low temperatures. A few degrees in differences among various materials is not likely to bring big benefits in where the seal can be used. Big differences in low temperature performance is what we see on this slide. Getting back to the sour resistant materials we discussed earlier, the materials represented on the graph are as follows. The FEPM is the green line, the FFKM is the blue line, and the low temperature FFKM is the red line. We can observe that the red line, or low temperature FFKM, is significantly lower in glass transition than the other 2 materials, with about a 25 to 30 degree decrease in the glass transition. This is enough of a difference that allows this type of elastomer to be used in seals for subsea applications or in cold parts of the world for surface equipment. To demonstrate this concept in a more tangible way, we can observe a durometer measurement on the materials at low temperatures. Here on this graph, the FEPM is the red bar, the FFKM is the blue, and the low temperature FFKM is the green bar. As you might expect, as the temperature decreases, the durometer will increase. Comparing to the glass transition we saw on the previous slide, the low temperature FFKM will still indent with the durometer at minus 25 degrees C, which is just above its glass transition, while the other 2 materials will not indent with the durometer, and therefore giving a maximum reading. I have 3 case studies to show where this low temperature FFKM technology of sour gas resistance and low temperature performance has been used in oil and gas applications. For this case study, we have body seals for an upstream oil and gas ball valve. Now the application, as I just mentioned, is a large ball valve body seal for upstream service. Now the problem is that an oil company operator required an elastomer sealing solution for a valve that can stand minus 30 degrees C low temperatures, high pressures, with resistance to 25% H2S for a very long service. They already knew that HNBR O-rings had failed in service, creating a hazardous situations. Now the PPE solution was to provide a low temperature FFKM in the form of customized sized O-rings for the large ball valves, which were greater than 24 inches. And we conducted third-party testing to confirm the long-term stability in sour gas conditions at the 25% levels. The outcome, the oil company solved a major safety concern and prevented costly downtime. For this case study, it's a tubing hanger plug for low temperature and high pressures. So the tubing hanger plug was for a downhole subsea application. The oil service company was looking for a sealing solution for an elastomer that has low temperature performance, high pressure resistance with resistance to H2S. PPE proposed a solution using the low temperature FFKM in the form of custom designed chevron stacks and O-rings with backup rings with testing prior to use for a live subsea requirement in the North Sea. Now the outcome was that the OEM company tested the seal arrangement successfully at 15,000 psi from a high temperature of 121 degrees C down to minus 10 degrees C, and then pushed the test by taking it even lower to minus 25 degrees C with a V0 or bubble tight seal, and verified on an independent test rig. This case study is for breakaway subsea connectors. The application is a subsea connector that would disconnect in emergencies from surface vessels. Now the problem was getting a bubble tight connection from minus 18 degrees C to 121 degrees C with resistance to H2S in multiple fluids such as oil, methanol, and corrosion inhibitors, and be 15,000 psi pressure capable. PPE proposed a custom seal which was developed with Perlast Ice G90LT with peak backup elements. The design from concept, manufacturing, and test validation was very fast, lasting about 6 months. The outcome is that the OEM equipment manufacturer successfully tested the equipment to API 6A PR2 requirements and deployed the equipment globally. Now I'll finalize the presentation with some conclusions. We saw this table earlier in the presentation. If we look at both sour performance and where there is significantly lower glass transitions, there really is only one material that is capable of performing in both situations, which is low temperature FFKM. All of the other materials will either sacrifice low temperature performance or sour performance. Low temperature FFKM is a relatively recent technology that many don't know is available, but can give an engineer a lot of capability and give the end user the reliability needed for the oil and gas industry. Low temperature elasticity and sour gas resistance has been a problem in the past, but not anymore. Low temperature FFKM, Perlast Ice, has been successfully used in critical oil and gas applications where high pressure, high temperatures, low temperature, and sour performance is required. For additional information, we have a number of technical papers and brochures available on our website, www.prepol.com. That concludes the presentation. I'll now turn the meeting back over to the moderator for any questions.
Thanks, Steve, for your insight into the field of low-temperature elastomer seals for sour gas. So now let's get started with the Q&A. We'll have about 20 minutes for questions, but if we don't get a chance to answer your question, don't worry, we'll respond with an answer for you within 24 hours. The complete Q&A transcript, including answers we did not have time for, will be posted with the webinar when it goes into the on-demand mode. Okay, so here's our first question. What is the maximum level of H2S that a low temperature FFKM can handle?
Yeah, that's a great question. We've essentially believe that the low temperature perfluoroelastomer FFKM is inert to H2S or sour gas. We have test data that shown testing to the NORSOC type protocol, but with the gas composition of 25% H2S, 3% CO2, and 72% methane at temperatures up to 175 degrees, and we've really seen no detrimental effects to the physical properties. So we feel very confident that the perfluoroelastomer, the low temperature perfluoroelastomer, doesn't react with sour gas.
Okay, thanks, Steve. Here's your next question. Has the low temperature FFKM material been qualified for RGD?
Yeah, that's a great question. We typically test to the industry standards. A lot of people are aware of them, but you have the NORSOC M710 Annex B. There's a NACE TMO 297 and the ISO 23936. So we've tested to all of those standards, and I believe the NORSOC M710 is one of the more aggressive standards out there, and we have achieved a passing rating to the NORSOC M710 rating with the low temperature perfluoroelastomer.
Okay. What would be the HT test conditions?
Yeah, I think this may be referring to the presentation. What we tested was 25% H2S in the NORSOC protocol, and we've tested 25% H2S up to 175 degrees C.
Okay, thanks, Steve. What is the hardness of the low temperature FFKM material you mentioned?
We have several versions available depending on the application. The particular grade we tested, and then is shown in the data, is a 90 Shore A material designed for high pressure oil and gas applications.
Okay, thank you. Just a follow-up question to what we were discussing earlier. The RGD rating after aging in HPHT conditions, is that in a particular test fluid?
The RGD testing, we've conducted a number of tests. The NORSOC M710, for instance, is just a gas test. So the standard gas percentage, the 90% methane and 10% CO2.
Okay, thank you. We've got lots of questions coming in now, so here's your next one. Has PPE characterized the influence of the seal design into the low temperature performance?
Yes, the geometry and the seal design is very important to the overall performance, especially in low temperature. So it's hard to give a blanket answer, but yes, we've conducted and conduct tests most often with our customers, because every seal design is usually unique, but the influence of the cross-section, the squeeze, and other factors of the hardware do play a significant impact as far as the low temperature rating. So perhaps the generic answer is we have tests, we've done them with with specific customers, but oftentimes we do need to work individually to understand the entire scope of what the seal looks like in the hardware to make a good estimate.
Okay, thank you. Has any life estimation or prediction been performed on any of the seal materials?
Yeah, so that's a really good question that the industry has been looking at. Most often we refer back to, let's just call it the NORSOC M710, which describes the method of using the Arrhenius equation. You know, as described in the spec, it's not always a straightforward answer using the test procedures that are in the industry, using things such as tensile, strain, or elongation. What I like to do in the absence of having a good methodology is trying to look at long-term aging studies and really seeing if you see a steep decline in properties such as modulus or elongation. And in my mind, that would give a pretty good indication of whether the material is resistant or not to the test fluid. But I do agree that the lifetime prediction is something that's needed in the industry, and is something that I know a number of companies, including PPE, are working on.
Okay, thanks, Steve. Does FFKM work well in ethanol gasoline mixtures?
Yes, for sure. The perfluoroelastomers are inert to most fluids, especially aromatic hydrocarbons, just oil, fuels, and all alcohols.
Okay, so we've only got time for a couple more questions. So here's the next one. What is the maximum H2S concentration that the FKM material V91J might withstand for 1,000 hours? Are there a few 100 hours ppm that are detrimental to its performance in a short service life?
Yeah, I think, in my opinion, that in the parts per million range, there's generally not too much of a concern with using a high-quality fluoroelastomer, especially a peroxide-cured fluoroelastomer. In my experience, the biggest problem with fluoroelastomers in any kind of H2S is the temperature at which it's exposed. The data that I've seen and worked with in the past suggests that as you really start to approach temperatures over 150 degrees and especially 175 degrees, when you're in a higher concentration of several percent, you can reasonably quickly see some detrimental effects. But I think when you're at the parts per million level at a temperature, let's say 175 degrees and lower, you can have quite a long life with an FKM.
Okay, I think the next question might be sort of related to the previous question. Is there a low threshold for H2S where it becomes a non-factor, where at a low ppm you will not see damage to your elastomers? Because much of the chemical compatibility data that's available is ranked on a 1 to 4 scale, or poor to good performance, without considering the percentage of H2S?
Yeah, perhaps related to the last question, I think it's very difficult to, at a ppm level, see any, in a lab environment, it would take quite a while to see a detrimental effect. So the biggest factor is not always the concentration, but the temperature in the data that I've seen. So that's what ages the elastomer most in the presence of H2S, not necessarily the concentration, but the temperature. So again, if you're below about 175 degrees in a ppm, 175 degrees C in a parts per million environment, a good quality FKM will likely hold up.
Okay. What are the typical compression set values?
Yeah, these days with the modern perfluoroelastomers, those that have been on the market, say in the last 10 years or so, most of them have reasonably good compression set values. So let's just say on an O-ring test, 70 hours, 200 degrees C, I would expect to see a compression set around 25%. And that would be in hot air.
Okay, thanks, Steve. And here's your last question. In low temperature applications, is the H2S reaction rate fairly low and less likely to cause a problem?
Yes. Now, we've not actually tested in very low temperatures H2S resistance. Usually the idea behind the testing is to greatly accelerate the test. So we like to test at as high as possible temperature to essentially shorten the test period. And if you're at certainly lower temperatures, especially room temperature and below, it's going to take a long time to see an effect on a lot of elastomers. But it's something that you don't see in the literature very much, and we haven't tested it.
Okay. Well, thanks, everyone, for your questions. We're going to have to wrap this webinar up now. So, Steve from Precision Polymer Engineering, thank you for spending some time with us all today. For everyone listening, to find out more information on low-temperature sealing solutions, please visit the PPE website, and as always, feel free to call or email us with any questions or queries.